Let's solve the following problem. Apply either the ratio test or the comparison test to investigate the convergence of the following series. The series we have to consider is the sum of the square root of k plus 1 minus the square root of k minus 1, with k going from 1 to infinity. Okay, so we have to first try to get an idea for this series, how it behaves, whether we can expect it to converge or not. For that, we have to look at the general term. I will denote this term by ak. So let me look at this difference of square roots, the square root of k plus 1, k squared plus 1 and k squared minus 1. Well, you might recall that we had a good way of dealing with expressions such as this, where we have the difference of two square roots, and the way we have dealt with them is to take them and multiply this expression by 1 in a tricky way, that is to take the sum of these two square roots and multiply it by that sum, but of course we also have to divide by that sum then, just to make it right, make this expression, this equality, true. So what do we get then? Well, let's look at the numerator. What we have there is an expression of the form a minus b times a plus b. So remember, here we use the classic identity, that is a minus b times a plus b is a squared minus b squared. And if we do that in the numerator, what we will get, now let me write it over there. So this is a long equal sign. What we will get is a squared minus b squared. So a squared is k squared plus 1 in this case, and b squared is k squared minus 1. So k squared plus 1 minus k squared minus 1 divided by that sum of square roots. And in the numerator, what magically happens is the k squared terms cancel, and we'll get 2 divided by the sum of the square roots. Now that's already something, because now what we have is, for the general term, we still have the general term. This is ak, written in a slightly different way, but in a way which allows us to say that ak, which is equal to this expression now, 2 over the square root of k squared plus 1 plus the square root of k squared minus 1. Now for large k, just to get an idea of how these terms behave for large k, this is roughly the same thing as saying 2 divided by the square root of k squared, because adding plus 1 to the square of a large number doesn't really make a difference when we take the square root, so it's basically the same thing as just taking the squares without adding or subtracting 1. But that, of course, is 2 over k plus k, which is 1 over k. So we expect, well, the general term to behave for large indices as the terms in the harmonic series. Okay, remember, the harmonic series is the sum of these numbers, 1 over k, with k going from 1 to infinity. So this series roughly behaves like the harmonic series, so we expect divergence. We expect our series to diverge. Okay, how should we do that? Well, we have to go back to this general term of our series and find some rigorous proper proper bounds for any k, any index k. Well, let's do that. So we have 2 divided by the square root of k squared plus 1 plus the square root of k squared minus 1. Now, we want something, in order to show divergence, what we would like is to get a smaller number that still behaves like 1 over k. Okay, so how do we get something that's smaller, that's less than or equal to this expression? Well, we have to increase the denominator. How do we do that so that we are moving towards 1 over k? Well, we want to have some k squared by itself. Well, we can't do that. In order to have k squared in here that is a greater number, so we get a smaller ratio, is the only way, well, certainly one good way to do that is to replace that plus 1 by plus k squared. That definitely is going to give us a larger denominator and a smaller ratio. What about the other term? There, simply just removing minus 1 will give us a number that is greater, the square root of k squared is greater than the square root of k squared minus 1, so the ratio is again getting smaller because we increase the denominator. So let's look at this expression. That's 2 divided by the square root of 2k squared plus k. The square root of 2k squared can be written as root 2 times k. So this whole thing can be written as in the denominator as root 2 plus 1 times k. That is what we have. So this is only a number times just a constant times 1 over k. So what we have found is that our original series has this smaller comparison series with this general term, and this smaller comparison series is just a multiple of the harmonic series. Hence, by the comparison test, let me just say CT, comparison test, the series diverges. And this is the solution of this problem.